Hello, my sleepy friends, and welcome back to Hafiz Sleep. If you're joining me for the first time, a very special welcome to you. This is the place where we calm our busy minds by wandering through the most fascinating and peaceful corners of science. Tonight, we're going on a journey to the very edge of reality itself to ask a question that sounds like pure science fiction, but is a genuine puzzle at the heart of physics. Can time run backward? Think about your day. You woke up, you made a cup of tea or coffee, you might have spilled a little milk. You saw it spread across the counter, a white pool growing. You didn't see it gather itself back into the carton. In our world, time has a very clear direction, an arrow. We remember the past, we anticipate the future, and events seem to march irreversibly forward. Spilled milk doesn't unspill. A shattered glass doesn't reassemble. This feels like a fundamental rule of the universe. But what if I told you that this rule, this relentless forward march of time, might be an illusion? Or at the very least, a consequence that only emerges when you look at the big, messy, complicated world around us? What if, when you zoom in to the universe's most basic ingredients, to the realm of quantum particles like electrons and photons, the script of time isn't so rigidly written? What if, at that level, the laws of physics are perfectly happy for events to run forward or backward? This is the profound mystery of microscopic reversibility. Before we dive into the quantum strangeness, we need to understand the classical idea. The principle of microscopic reversibility is an old and elegant idea in physics and chemistry. In its simplest form, it states two things. First, at the level of individual particles and their interactions, the equations that govern their motion, whether Isaac Newton's laws or later Erwin Schrödinger's quantum equation, are symmetric in time. This means if you were to make a perfect frame-by-frame recording of two atoms colliding and bouncing apart, and then you played that recording backward, the reversed movie would also be a perfectly valid solution to the equations of motion. There's no inherent play button in the math. The second part of the principle is a statistical consequence. In a state of equilibrium, like a gas where temperature is uniform everywhere, every single molecular process happens at exactly the same average rate as its reverse process. For every collision that sends particles one way, there's a corresponding reverse collision that undoes it, and at equilibrium, these are perfectly balanced. This principle is incredibly powerful. It's the reason we can derive fundamental relationships like the equilibrium constants in chemistry. It tells us that a movie of atoms jiggling in a crystal at equilibrium would look completely normal whether played forward or backward. The Austrian physicist Ludwig Boltzmann used this idea in the 1870s to build his statistical understanding of thermodynamics. He showed that while each tiny collision is reversible, the mind-boggling statistics of countless particles give rise to the irreversible increase of entropy, the famous second law of thermodynamics. So, from perfectly reversible microscopic rules, our irreversible macroscopic world emerges. It's a stunning piece of scientific insight. Now, this is where our story takes its first strange turn. For a long time, physicists believed these symmetries, the idea that the laws of physics look the same in a mirror, parity, or if you swap matter with antimatter, charge conjugation, or C, and if you reverse the flow of time, T, were sacred. They were beautiful mathematical pillars holding up our understanding. So picture the scene in the physics world up to that point. It was like living in a perfectly symmetrical, beautifully constructed house. The walls were straight, every room had its mirror image, and the architects, our equations, promised this was how the universe had to be built. The symmetry of parity, the idea that the mirror image of any particle interaction should happen just as easily as the original, wasn't just a rule, it was a cherished pillar of reality. It felt obvious. The laws of physics shouldn't care about left and right any more than they care about whether you perform an experiment facing north or south. It was a deep-seated belief woven into the fabric of what scientists thought they knew. Then, along came these strange particles called kaons. They were like enigmatic guests who didn't follow the house rules. Scientists observed that neutral kaons could decay in two different ways, with two different lifetimes, which, according to the impeccable logic of parity, suggested something absurd, that the same particle could have two intrinsic handednesses. It was as if a single, perfectly normal coin, when flipped, could sometimes land as a head and sometimes land as a tail, but also sometimes land with the head facing a completely different direction in a mirror world. This wasn't just a quirk, it was a glaring, uncomfortable puzzle that threatened to crack one of the beautiful pillars. This is where our two young physicists, Tsung-Dao Lee and Chen-Ning Yang, stepped in. Instead of trying to force the strange kaon behavior into the old symmetrical box, they dared to ask a radical, almost heretical question. What if the problem wasn't with the kaons, but with the rule itself? Specifically, what if the force responsible for their decay, the weak nuclear force, simply didn't obey the law of mirror symmetry? What if the weak force could tell the difference between left and right? It was a stunning proposition. They weren't just suggesting a new particle or a tweak to an equation. They were suggesting that one of the fundamental forces of the universe had a preferred direction, a cosmic left-handedness. But in physics, a bold idea needs a brilliant experiment to test it. Enter Chien-Shiung Wu, the First Lady of Physics. Her experiment, which you mentioned, is a legend for its elegance and precision. She took radioactive cobalt-60 atoms and, at temperatures near absolute zero, used a magnetic field to line them all up like tiny spinning tops, all rotating in the same direction. Think of them as billions of identical spinning carnival rides. If parity symmetry held, when these cobalt nuclei decayed by spitting out electrons, those electrons should have flown away equally in all directions, up, down, and sideways relative to their spin. There should have been no preferred exit door. But that's not what happened. Wu and her team watched as the electrons consistently fled in one particular direction, opposite to the direction of the nuclear spins. It was a dramatic, undeniable preference. The mirror had been shattered. The image in the looking glass was not the same as reality. In the mirror world of that experiment, the electrons would have flown out in the opposite direction, which simply didn't happen in our world. For this revolutionary discovery, for proving that the weak force violates parity, Li and Yang received the Nobel Prize with breathtaking speed just a year later in 1957. Now, the physics community was reeling, but trying to restore order. The immediate thought was, okay, P is broken, and we also quickly learned that charge conjugation, C, the symmetry that swaps particles and antiparticles, was also broken by the weak force. But maybe, the theorists hoped, if you combined the two broken symmetries, you'd get a perfect restored one. Maybe the universe, when viewed in a mirror and with all matter swapped for antimatter simultaneously, would still behave the same. This combined symmetry was called CP. It was a new hope for a deeper, hidden order. For a few years, CP symmetry was the new sacred pillar. That is, until 1964, when James Cronin and Val Fitch performed their now famous experiment with neutral kaons. They found a tiny but monumental effect. A certain type of kaon decay that should have been absolutely forbidden if CP symmetry were perfect was actually happening. Very rarely, but it was happening. CP was not the inviolable rule either. This was the second great shock. It won them the Nobel Prize in 1980 and opened a door to one of the greatest mysteries in all of science. Why is this CP violation such a big deal? Because it connects the infinitesimally small world of particle decays to the cosmic scale story of our very existence. As Andrei Sakharov later realized, one of the essential ingredients needed to explain why our universe is made almost entirely of matter and not an equal mix of matter and annihilated radiation is a process that treats matter and antimatter slightly differently. CP violation is exactly that, a process where a particle and its antiparticle decay at slightly different rates. That tiny imbalance in the early universe could have been the seed that led to everything we see: stars, planets, us. Without it, we likely wouldn't be here to ponder it. But our story has a third and perhaps the most profound actor waiting in the wings: time reversal symmetry, or T. This is the idea that if you could reverse the flow of time, like hitting rewind on a movie, all the laws of physics would still work perfectly. The flipped movie would look just as valid as the original. After the fall of P and then CP, a critical question arose: is T-symmetry also broken? Here is where we encounter one of the most powerful and beautiful theorems in modern physics, the CPT theorem. This isn't just a hypothesis, it's a mathematical cornerstone. It states that in any consistent local quantum field theory that respects special relativity, which our best theories of particle physics are, the combined symmetry of CPT must always hold. It's considered an exact symmetry of nature at the most fundamental level we know. What does CPT mean? It says that if you take our universe and simultaneously do three things: 1. Swap every particle with its antiparticle, C. 2. Reflect it in a mirror, P. And 3. Reverse the flow of time, T. You will get a universe that evolves exactly according to the same physical laws as our own. An antimatter, mirrored, time-reversed version of our cosmos would be, according to the laws of physics, perfectly valid and indistinguishable in its operation from ours. This theorem has a monumental consequence. It tightly links C, P, and T into a triple package. They are a team, and the theorem says the product of all three must always equal 1 or be conserved. Think of it like a cosmic ledger that must always balance. Now, if experiments show that CP is violated, that the CP part of the product does not equal 1, then the ledger is out of balance. The only way to restore the mandatory balance of CPT is if the T part is also not equal to 1. In other words, if CP is violated, then T must also be violated to preserve CPT symmetry. It's a direct mathematical implication. The theoretical hint that time's arrow might be written into the laws at a fundamental level. The discovery of CP violation by Cronin and Fitch was, by the ironclad logic of the CPT theorem, also the discovery of time reversal T. It meant that certain microscopic processes in particle physics have a preferred direction in time. They happen at a slightly different rate forwards in time than they would if you ran the movie backwards. Now, let's pause and really unpack this, because it's easy to get swept up and think we've found the secret to time's arrow, the reason we remember the past and not the future, why milk mixes into coffee but never unmixes. But we have to be very careful here. The T violation we're talking about in particle physics is not the arrow of time we experience in our daily lives. The T violation in processes like kaon decay is subtle, statistical, and most importantly, reversible. It's about probabilities. It means that if you watch a swarm of kaons, the rate at which they oscillate into their antiparticle state is ever so slightly different from the rate at which the antiparticles oscillate back. But the process can still go both ways. Information isn't lost. It's like a game of chance, where the odds of moving from square A to square B are 50.001%, and the odds of moving from B back to A are 49.999%. There's a bias, but the game still goes back and forth. Our macroscopic arrow of time, the irreversible increase of entropy, is a different beast entirely. It comes from statistics on an unimaginable scale, from the overwhelming probability that disorder increases. You never see a shattered glass leap off the floor and reassemble itself because the number of disordered states for those molecules is astronomically larger than the number of states that look like a tidy glass on a table. This arrow emerges from countless interactions, not from a tiny bias in a single quantum process. So, the T violation implied by CP violation and the CPT theorem is a fundamental, fascinating, and deep feature of the laws of physics. It tells us that the script of the universe is not perfectly time-symmetric at the most basic level of the weak force. It gives us a crucial ingredient for our own existence as matter-based beings, but it is not the engine that drives the one-way flow of time we feel in our bones. That engine is still the ancient, stately, and overwhelming drive of entropy, starting from a special low-entropy state at the birth of our universe. To make this cosmic balancing act of CPT a little more tangible, let's imagine a simpler analogy. Imagine you have a special magical safe with 3 combination locks on it: a red lock, C, a blue lock, P, and a green lock, T. The rule of the universe, the CPT theorem, says that the only way to open the safe and see the true, valid contents of physical law is if the product of all 3 lock settings is 1. Maybe 1 means all dials are aligned just right. For a long time, physicists thought each lock could be set to 1 individually. They thought P was 1, C was 1, and T was 1. Then, through Wu's experiment, they discovered that when you look at the weak force, the blue P lock is actually set to -1. It's flipped. The mirror image is wrong. They quickly found the red C lock was also -1. 2 negatives multiplied together make a positive. So they thought maybe the combination CP, red and blue together, gives +1. Maybe the safe opens if we just use 2 locks. Cronin and Finch's experiment showed, nope, even the CP combination is slightly off. It's not perfectly +1, it's something like 0.999999. There's a tiny, crucial flaw. But the universal rule says the product of all 3, CPT, must be exactly +1 to open the safe and have a consistent universe. The only mathematical way to fix it is if the third lock, the green T lock, is also not perfectly +1. Its setting must be the exact reciprocal of the CP setting to make the total product come out to +1. If CP is 0.999999, then T must be 1.000001 to compensate. That slight deviation in T is time reversal violation. It's not that time is wildly broken, it's that it has a tiny bias, a subtle leaning, which is the exact counterpart to the bias between matter and antimatter we see in CP violation. This is the elegant, interlocked dance of symmetries that the mid-20th century revealed. We moved from a world of assumed perfect mirrors into a richer, more interesting, and slightly lopsided reality. We learned that the weak force is left-handed, that matter and antimatter are not perfect mirror twins in all ways, and that because of this, the flow of time itself has a faint, fundamental bias written into the laws of quantum particles. It's a bias that doesn't make our watches run forward, but it might just be the reason we, and all the matter we're made of, are here to wonder about it in the first place. The search for the source and size of this CP, and thus T violation, continues to be one of the most exciting frontiers in physics, from giant particle colliders trying to catch B mesons in the act, to ultra-precise experiments trying to measure the shape of a neutron with unbelievable accuracy. Every new piece of the puzzle brings us closer to understanding not just the particles, but the very story of our asymmetric cosmos. Let's pause here. We've seen that in our big world, time is irreversible. We've seen hints from particle physics that time reversal symmetry, T, might be fundamentally broken. And yet, we started by saying that at the quantum level, things might be reversible. This seems like a contradiction. Welcome to quantum mechanics, where holding 2 contradictory ideas in your head is often the first step to understanding. This brings us to the cutting edge. Recent years have seen mind-bending experiments that explore time in the quantum realm. One of the most evocative comes from researchers at the Austrian Academy of Sciences and the University of Vienna. The work from Vienna and the Austrian Academy of Sciences is some of the most direct, hands-on tinkering with the concept of time we've ever seen. But to really appreciate the magic trick they're performing, we need to understand the tools in their quantum toolbox. The two stars of the show are superposition and entanglement. You might have heard these terms before. They're the rock stars of quantum weirdness. But let's see what they really mean in the context of our little photon's journey. First, superposition. In our everyday world, a switch is either on or off. A coin is either heads or tails. A photon, in a classical sense, would be in one specific state. But in the quantum realm, a particle like our photon can exist in a superposition of states. It's like that coin. While it's spinning in the air isn't heads or tails, it's in a strange, fuzzy, probabilistic blend of both possibilities. It only becomes definitively one or the other when we catch it and look, which is the act of measurement. This means that before it's measured, a quantum system holds a multitude of potential futures within it, all coexisting. It's this fundamental property that gives the quantum world its fluidity and is the first crack in the wall of rigid, forward-only time. Then there's entanglement. This is the phenomenon that Einstein famously called spooky action at a distance. When two quantum particles become entangled, they lose their individual identities. Their properties become linked in such a profound way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. It's as if you had two magical coins. You spin them together in a special way and then send one to the other side of the galaxy. When you stop your coin and see its heads, you know, faster than light, that the other coin is tails. They're not communicating, they're two parts of a single, non-local system. These two ideas, superposition of states and spooky connections across space, are the raw materials. The Viennese researcher's genius was in asking, if we can entangle particles in space, can we entangle events in time? Can we create a superposition not just of where a particle is, but of when certain things happen to it? This is where their remote control, the quantum switch, comes into play. Imagine you want to do two things to our photon. Let's call them Operation A and Operation B. In the classical world, you have to do them in an order, either A then B or B then A. The final state of the photon will be different depending on which order you choose. It's like putting on your socks and then your shoes. The final result is very different from shoes then socks. A quantum switch puts these operations into a superposition of orders. It doesn't do A then B. It doesn't do B then A. It puts the photon through a configuration where the sequence of events itself is in a fuzzy, blended state. Did A happen before B? Did B happen before A? The answer is yes. The causal order, what we think of as the unbreakable logic of cause preceding effect, becomes indefinite. Think back to Miguel Navascuez's wonderful analogy. In the classical movie theater of our daily lives, the film runs from start to finish. You can't watch scene 20 before scene 10. The projector is stuck on play. But with a quantum remote control, you can put the very sequence of events into a superposition. The movie player is in a state where it is both playing scene 10 then 20 and scene 20 then 10. It's this control over the order of events that is the key to the whole trick. So, how does this lead to rewinding? Let's walk through the experiment in a bit more detail. They take a single photon, our simplest quantum bit or qubit. They prepare it in a specific known starting state. Then they send it on a journey through a special crystal. As it travels, it evolves. Its quantum state changes, just as we change as time passes. In a normal, classical process, that evolution would be a one-way street. But here, they use the quantum switch. They don't just let the photon evolve, they couple its evolution with another quantum system, often another photon or an internal degree of freedom, in such a way that the two become entangled across time. They create a scenario where the final state of the combined system is mathematically linked to the possibility of the original photon state being restored. Through precise manipulation, they can then perform a measurement on the auxiliary system, and, because of the spooky, probabilistic magic of quantum mechanics, this measurement can force the original photon to snap back to its starting state. Crucially, it doesn't retrace its steps. You don't see the photon's state change back gradually through all the intermediate points. It's more like a teleportation back to a previous point in its own history. The photon returns to its original, previous state before it made the journey in any classical sense. The journey, in a way, gets erased from its quantum resume. This is why it's not time travel in the science fiction sense. We're not sending matter or energy backwards. We're not creating a paradox where you can go back and meet your grandfather. What we are doing is manipulating information. A quantum state is a packet of information. This protocol allows us to reset that packet of information to a previous version. It's the ultimate undo command for a quantum calculation. And the limitations are what keep it from being world-breaking. The researchers themselves point out the mind-boggling scale of information in a macroscopic object like a human being. Every atom, every chemical bond, every neural firing pattern represents a bit of information. To rejuvenate a human system by 1 second, to reset all that information to its state 1 second ago, is a computation of staggering, universe-spanning complexity. They estimate it would take millions of years with any conceivable technology. So while the principle whispers that time's flow is malleable, the practice shouts that for our world of coffee cups and memories, the arrow of time remains a powerful emergent reality. But let's talk about the most fascinating twist of all, which is the relationship between this rewinding and the act of measurement. In quantum mechanics, measurement is not a passive act of looking. It is an aggressive, disruptive interaction. It's the moment you catch that spinning coin. Before you look, it's in a superposition of heads and tails. The instant you look, it becomes definitively heads or tails. The act of observation collapses the beautiful fuzzy wave of possibilities into a single concrete fact. This is the golden rule of the quantum rewinding protocol. To rewind perfectly, you must not have peaked. If you track the photon's exact path, if you measure its state at any point during its journey, you lock it into a single history. You collapse the superposition that makes the rewind possible. You turn the quantum movie back into a classical one, glued to the projector of cause and effect. The protocol works precisely because it is blind. It doesn't need to know the internal details of how the photon's state changed. It doesn't need a step-by-step log of the errors. It sets up the quantum circuit, makes the final, clever measurement on the entangled partner, and lets the probabilistic laws of quantum mechanics do the rest, forcing the system to snap back to a prior configuration. It's like fixing a complex machine by giving it a single, precisely calibrated shake rather than taking it apart screw by screw. The shake only works if you haven't already taken the machine apart to inspect it. Now let's talk about going the other way. Navasquez and the team also explored how to make a quantum system age faster. His explanation is brilliantly intuitive. He says that to make one system age 10 years in 1 year, you need to find the other 9 years from somewhere. In a year-long experiment with 10 identical quantum systems, you could, in a sense, steal 1 year of evolution from the first 9 and give all that borrowed time to the 10th. At the end of the year, the 10th system will have experienced 10 years worth of change, while the other 9 will be frozen, unchanged from when you started. This isn't about moving into the future, it's about accelerating processing. Imagine you have a very hard calculation to perform that naturally takes a quantum computer 10 years. With this kind of temporal resource management, you could, in principle, spread the cost across many quantum processors, getting your answer in 1 year by using 10 of them in this coordinated, time-borrowing way. It reframes time as a kind of currency that can be saved, spent, and transferred between systems, at least in the insular economy of the quantum lab. So, to come back to our big question, is this time reversal? As the researchers say, it's more accurate to call it time translation or state manipulation. They are not reversing the flow of time in the universe. The clock on the wall keeps ticking. Their coffee still goes cold. But within the isolated, exquisitely controlled universe of their experiment, they can make a quantum system behave as if it has moved to a different point on its own timeline. They can make its present look like its past. What this shows, more than anything, is the plasticity of the quantum rulebook. The laws at this level don't insist on a narrative. They don't demand that story goes from beginning to middle to end. They simply govern probabilities and connections. Our classical experience of irreversible time, of spilt milk and fading echoes, emerges from the statistics of countless such quantum events, from the loss of information into vast environments, and from that special low-entropy starting point of our universe. But peel back the layers, isolate a single particle from the noise of the world, and you find that the foundational script allows for scenes to be played out of order. It allows, in a very specific and limited way, for the rewind button to exist. This is the quiet, profound revelation from Vienna. It's not a technology for building time machines. It's a deeper insight that the apparent rigidity of time is a consequence of scale and complexity, not a fundamental dictate. In the quantum realm, the remote control is on the arm of the chair. The film is not just playing, it's waiting for its instructions. And in learning to give those instructions, we're not just learning to correct errors in a future quantum computer. We're learning the first verbs of a new language for describing reality itself. So, my friend, we've been on quite the journey together, haven't we? We've shattered cosmic mirrors, watched a physicist in New York rewrite the rules of left and right, and even seen a single photon in Vienna get a taste of its own past. These were all glimpses of time's strange and layered nature. But now, we need to take a step back and get formal. We need to build a proper principle, a foundational rule of the universe that can account for all this strangeness. We've been dancing around it. It's time to meet it head-on. This brings us to the formal principle of quantum microscopic reversibility. Now, the word microscopic reversibility might sound intimidating, but the idea behind it is one of the most elegant and powerful in all of science. At its heart, it's a statement about fairness and balance at the smallest scales of reality. It connects the timeless laws of motion to the world of probabilities we see when we watch a million particles at once. But before we can understand why it had to go quantum, we absolutely must appreciate the classical version, the original masterpiece. Imagine, if you will, a perfectly closed box filled with a gas. This box is in perfect equilibrium. Its temperature is uniform, its pressure is the same everywhere. It's a state of complete rest at the microscopic level. But rest here is a trick of the eye. Inside, billions of molecules are screaming around in a chaotic frenzy, a high-speed ballet of collisions. Now, let's pick out just one single specific event in that ballet. Let's focus on two molecules, molecule A and molecule B. They're flying towards each other on a collision course. They meet, they exchange energy and momentum with a tiny ping, and they fly off in new directions. This is the forward process. Now, the principle of microscopic reversibility in classical physics makes a stunning claim. It says, in our box of gas at perfect equilibrium, for every single collision like that one, there is an exactly equal chance of seeing its perfect reverse. That is, there is a collision happening somewhere, right now, where the two molecules are starting from the exact endpoints of our first collision, with their velocities perfectly reversed. They fly towards each other along the precise backward paths. They meet, they exchange energy and momentum, and they fly apart to land in the exact starting positions of our first pair. It's the movie played perfectly in reverse, frame by frame, and it's happening just as often. Why is this such a big deal? Because it takes the beautiful mathematical time symmetry of the laws, like Newton's equations, and translates it into a statistical rule for the real, messy world. It says that at equilibrium, the cosmic ledger is perfectly balanced. Every single microscopic transaction has an equal and opposite transaction happening at the same rate. This isn't just a neat fact, it's the bedrock of all statistical mechanics and thermodynamics. It's the reason we can derive fundamental things, like the exact relationship that tells you how much product you'll get from a chemical reaction when it settles down. It's a principle that has stood for over a century, a pillar of our understanding of how the world works when left to its own devices. But And you knew there was a but coming. This elegant picture is painted on a canvas of certainty that simply doesn't exist in the quantum world. The classical principle makes a crucial hidden assumption that we can know, or at least in principle know, the exact story of each particle. To say that the reverse collision is the exact mirror image, you need to be able to pin down the starting and ending points with absolute precision. You need to know the exact position and the exact momentum of each molecule at every instant to map its perfect deterministic trajectory. You need to plot a single clear line through phase space, that abstract map that charts a particle's position and momentum. And here, my friends, is where the quantum universe throws a beautiful, inescapable wrench into the works. This is the domain of Werner Heisenberg's famous uncertainty principle. This isn't just a statement about measurement clumsiness, it's a profound declaration about the nature of reality itself. At the quantum level, a particle does not have a perfectly defined position and a perfectly defined momentum at the same time. The more you try to squeeze it into a specific point in space, the more its momentum becomes a blur of possibilities, and vice versa. A quantum particle doesn't travel on a neat, thin line like a train on a track. It's more like a wave of probability, a fuzzy cloud of could-be-here-ness that spreads out and evolves. It doesn't have a trajectory. It has a wave function. Think of the classical picture as a detailed black and white photograph of a single dancer in mid-leap. You can see the exact position of every limb. The quantum picture is more like a long exposure photograph of that same dancer taken in a dark room with a sparkler in their hand. You see the beautiful smeared-out path of light, the probability of where the sparkler was, but you cannot pick out a single sharp point on that path and say, this is exactly where it was at this exact millisecond. The path itself is the reality. This changes everything for microscopic reversibility. If you can't define a precise starting point in the quantum phase space, because a point requires exact position and exact momentum, then how can you even define what its perfect time-reversed twin looks like? The old, crisp definition falls apart in the quantum haze. The very stage on which the classical principle was built dissolves beneath our feet. But the quantum world doesn't just take things away, it gives us something new and spectacular in return. That something is quantum coherence. We've met this idea before with our photon in Vienna, but now we need to see it as the starring actor in our new principle. Remember superposition? A quantum particle can be in multiple states, multiple energy levels, for instance, at the same time. When it exists in a clean, phase-linked superposition of these states, we say it has coherence. It's not just either high energy or low energy, it's in a delicate humming blend of both, like a musical chord made of two perfectly tuned notes. This coherence, this quantum symphony, has a profound relationship with time. When you try to reverse the flow of events for a quantum system, this coherence doesn't just go along for the ride passively, it actively changes the odds. It interferes, like waves interfering in a pond, and this interference alters the probability that you'll see the time-reversed story play out. This was the brilliant insight of the international team from Italy, Korea, and the UK. They realized to bring the principle of microscopic reversibility into the quantum age, they couldn't just tweak the old equation. They had to rebuild it from the ground up using the language of wave functions and coherence. Their mission was to create a new quantum-corrected equation, one that would relate the probability of seeing a quantum process happen to the probability of seeing its time-reversed version. In their new formula, the simple balanced ledger of the classical world gets a new term, a term that quantifies the quantum coherence in the system. They showed something conceptually beautiful and a little surprising. The presence of quantum coherence between energy states makes the backward process less likely to happen compared to the classical prediction. The quantum symphony, it turns out, introduces a subtle bias against simply running the tape in reverse. The universe, at this fuzzy, fundamental level, has a tiny bit more trouble undoing things when those things are in a coherent superposition. The interference patterns work out in a way that slightly favors the forward direction of time's flow, not because of thermodynamics yet, but because of pure quantum mechanics. A beautiful equation on a blackboard is one thing, but physics lives and breathes in the laboratory. So how do you test a principle about time, reversibility, and quantum coherence? You build an experiment of exquisite simplicity and cleverness, and this team did just that, using the purest quantum system we know, light. Their experimental stage had two main characters. First, coherent state light from a laser. This is light in its most orderly, pristine quantum mechanical form. Think of it as the quantum equivalent of a perfectly tuned marching band, every photon in step with the others, their waves cresting and falling in unison. It's packed with quantum coherence. This laser light played the role of our quantum system, whose reversibility we want to study. The second character was thermal state light. This is the chaotic, disordered light from something like an old-fashioned light bulb filament. It's a jumble of photons of all different phases and energies, a cacophonous crowd with no rhythm. In the experiment, this thermal light played the role of the heat bath, the messy, warm environment that the pristine quantum system interacts with. By controlling the properties of this thermal light, they could effectively dial up or down its temperature. The plot of the experiment was elegantly direct. They brought these two beams of light together, the coherent laser light and the chaotic thermal light, and made them meet at a device called a beam splitter. This is like a half-silvered mirror that lets half the light through and reflects the other half. At this quantum crossroads, the two kinds of light mix, they interact. The orderly, coherent system touches the disordered thermal bath. Photons from the laser and photons from the bulb become entangled in a shared quantum state, their fates linked. Then came the detective work. They used a supremely sensitive technique called heterodyne detection to measure the light coming out of this interaction. This isn't just seeing if the light is bright or dim, it's a way to measure both the amplitude and the phase of the light waves with incredible precision. It's like having a microphone that can not only hear the note a violin plays, but also detect the exact shimmer of its vibrato. What were they looking for? They were watching for the fingerprints of time's arrow in these measurements. By carefully analyzing the statistics of the light they detected, the patterns in the noise, the correlations, they could calculate the probabilities for certain quantum transitions to happen in the forward direction, mixing the light, and compare them to the precise backward process. They could then pit their new quantum-corrected formula against the old classical one. The results were a clean and stunning victory for the quantum principle. Their new equation, the one with the coherence term, predicted the experimental results with perfect accuracy. The old classical equation was off. It was missing something. That something was the quantum coherence in the laser light and its effect on the dance of time reversal. But the most beautiful part of the whole experiment, the part that truly takes your breath away, was watching the transition happen in real time. The researchers had a control knock, the thermal light bath. When they made this bath very, very cold, meaning the thermal light was very weak and quiet, the quantum effects roared to the forefront. The deviation from the classical prediction was largest, the weirdness was maximum. In this frigid quantum regime, the system's coherence was preserved, and the new law of quantum microscopic reversibility ruled supreme. Then they began to turn up the heat. They made the thermal bath warmer and noisier. And as they did, something magical happened. The quantum weirdness began to fade away. The sharp, clear signatures of coherence were drowned out by the classical chaos of the warm bath. The experimental results began to slide smoothly and inevitably toward the predictions of the old classical equation. By the time the bath was hot enough, the system was behaving almost perfectly classically. The quantum principle had gracefully handed over the reins to its classical ancestor. This right here is one of the most profound demonstrations in modern physics. It's not just that the quantum world has its own rules, it's that we can build a bridge between those rules and our everyday experience, and we can watch someone walk across it. We can see the quantum to classical transition with our own instruments. The warm, noisy classical world of irreversible events and definite paths doesn't contradict the quantum world. It emerges from it, naturally and smoothly, when quantum coherence gets washed away by the buzz of the environment. The team didn't just prove a new principle, they filmed the origin story of our classical reality. So, what have we learned? The principle of microscopic reversibility, that sacred balance at the heart of equilibrium, is not broken by quantum mechanics. It is transcended. It grows and evolves into something richer and more nuanced. In the quantum domain, time's reversibility is not just about retracing steps on a map. It's about the interference of possibilities, the fragility of coherent superpositions, and a subtle, fundamental leaning that is written into the first draft of physical law. And the greatest comfort of all is that this strange new quantum principle contains the old one within it, like a seed contains the tree. When we warm things up, when we zoom out and stop looking so closely, the familiar, reliable world clicks back into place. The universe, it seems, has a rule book for every scale, and they are all, miraculously, chapters of the same story. Well, my friends, if our previous journey felt like peering into a quantum rabbit hole, then buckle up, because we're about to hop on a quantum roller coaster that loops through time itself. We've seen how single photons can be coaxed back to their past, and how the very rules of reversibility get a quantum makeover. Now, we encounter a concept so strange it sounds like the title of a lost sci-fi novel, the quantum time crystal. Let's break down this mind-bender step by step. Think of a beautiful, perfect diamond. Its shimmer comes from an incredibly orderly structure. The carbon atoms are arranged in a rigid, repeating pattern in space. That pattern is the crystal. Now, imagine taking that idea of order and repetition, but applying it not to space, but to time. Instead of atoms arranged in a grid, picture a system where its state, the arrangement of its quantum properties, undergoes a perfectly repeating cycle in time. It ticks like a clock, but a clock whose gears are made of quantum particles and whose winding comes from the fundamental laws of quantum mechanics, not from a spring you tighten. This is the wild idea first proposed by Frank Wilczek in 2012. A time crystal would be a quantum system in its lowest energy ground state, but instead of being still and featureless, it would be in a state of perpetual periodic motion. It's not gaining energy from anywhere, and it's not losing energy for friction. It's just ticking over forever in a loop. As one researcher put it, it's like a clock that runs forever without any batteries. Now, your alarm clock immediately springs to mind, and you think, that's a perpetual motion machine. That's impossible. And you're right to be skeptical, but the quantum world plays by a different set of rules. This isn't a machine that can do work or power a city. It's more like a quantum dance that never ends because it's already in the simplest, lowest energy dance move possible. Its entropy, its disorder, doesn't increase. It just stays constant, forever, locked in its rhythmic pattern. For years, this was considered a beautiful but impossible theory. The biggest roadblock was a powerful no-go theorem that seemed to prove such a thing couldn't exist in a stable equilibrium system. But physicists are a clever bunch. They found a loophole. They realized that if you couldn't have a time crystal just sitting there, maybe you could have one if you gave it a little nudge over and over again. This is the concept of a driven or floquet time crystal. Imagine you have a quantum system, like a chain of atoms, each with a property called spin that can point up or down. Now, hit this system with a regular periodic pulse from a laser, a steady kick. In a normal system, the spins would simply sync up with the kicks. If you kick it every second, it responds every second. But in a special type of driven system, something magical can happen. The spins decide to march to the beat of their own drum. They might only flip over completely after 2 kicks. They break the symmetry of the driving force itself. This period doubling is a hallmark of a discrete time crystal. The system develops its own robust internal rhythm that is locked in and protected by the quantum interactions of all its parts. It's this collective self-organizing behavior that makes it a true phase of matter, not just a fluke. And this is no longer just theory. Since 2016, teams around the world have been creating these exotic phases in labs. They've used chains of trapped ions, clouds of atoms, diamonds with special defects, and even the qubits inside quantum computers like Google's Sycamore processor. In one stunning experiment in 2022, physicists even linked two separate time crystals together, creating a two-level quantum system, a basic building block for future technologies. This brings us, at last, to that specific, jaw-dropping experiment from 2021 at the National Institute of Standards and Technology, NIST, that you mentioned. They didn't just create any time crystal, they created a 2D crystal of 150 beryllium ions held in place by electric and magnetic fields, a tiny, programmable quantum world. This crystal could vibrate collectively, like the skin of a drum. It also had a collective quantum property called spin. The genius of the experiment was to entangle the drum-like motion with the spin. Now, let's think about this setup as the world's most sensitive microphone. They let this entangled crystal listen to a fantastically weak external signal. The signal, like a faint whisper, would barely nudge the drum-like motion. But because that motion was quantum entangled with the spin, the information about that tiny nudge was imprinted onto the spin as well. Here's the problem. In quantum mechanics, measuring something directly often destroys the delicate quantum information. If they just measured the spin right away, they'd lose the signal in the noise. So, they performed their brilliant trick, time reversal. They didn't reverse time for the whole universe, of course. They applied a precise sequence of quantum operations that essentially ran the internal dynamics of their crystal backward. Think of it like this. You record a movie of a glass shattering on the floor. Then you play that movie in reverse, and you see the shards leap up and reassemble into a glass. The NIST team did something analogous to their quantum system. By reversing the dynamics, they disentangled the spin from the motion. As theorist Anna Maria Ray explained, this left the precious information about the faint signal, the displacement, stored cleanly on the collective spin property, where it could be read out with incredible precision. They turned their time crystal into an exquisitely sensitive quantum sensor. This isn't just a laboratory curiosity, this is the birth of a new tool. A sensor this stable and precise could listen for the faintest whispers in the universe, like the subtle signals from certain types of dark matter. Now, all of this incredible work, from the rewinding photons in Vienna to the ticking time crystals in Maryland, starts to paint a radical picture of time at the quantum level. It suggests that the flow of time as we experience it might be a kind of illusion, an emergent property that comes from looking at the big, messy picture. This brings us to the final piece of our puzzle, the 2025 research from the University of Surrey. These theorists were studying open quantum systems. This is a crucial phrase. Almost nothing in the real universe is a perfectly isolated quantum system. Everything interacts with a vast, messy environment. The air, stray light, the warmth of the room. This interaction is what usually destroys fragile quantum effects like coherence and entanglement, a process called decoherence. It's also what makes processes in our world seem irreversible. You never see smoke gather back into a cigarette. Heat never flows from a cold cup to a warm hand. This is the arrow of time we know. The Surrey team dug into the complex mathematics that describe these open quantum systems. Even when they used standard assumptions that typically lead to an irreversible arrow of time, they found something remarkable. A key mathematical component in their equations, called the memory kernel, remained symmetrical. Whether they plugged in a positive flow of time or a negative one, this kernel behaved the same way. What does this mean in plain language? Think of the memory kernel as describing how the quantum system remembers its interactions with the environment. The Surrey work suggests that at this deepest level of description, the quantum rulebook doesn't actually have a preferred direction for time written into it. The equations are still time-symmetric. The irreversible world we see emerges from the particular way we're entangled with the environment and the specific, overwhelmingly probable paths that chaos takes. As lead author Dr. Andrea Rocco put it, our overwhelming experience tells us time only goes one way, but we are just unaware that the opposite direction would have been equally possible. It's a matter of probability and perspective. Imagine watching a movie of an incredibly complex sandcastle being washed away by the sea. Playing it forward shows a natural, expected progression into disorder. Playing it backwards seems absurdly unlikely. But at the level of each water molecule and each grain of sand, the laws governing their collisions work perfectly well in either direction. The arrow is in the statistics, not the fundamental laws.
So, let's tie our quantum bow on this. We've journeyed from the shattering of mirror symmetry in the 1950s, through the remote control rewinding of photons, to the formal quantum principle of microscopic reversibility. We've now witnessed the creation of matter that crystallizes in time and seen how that very ticking can be harnessed to sense the cosmos. And finally, we see theoretical hints that the relentless forward march of time might be the universe's greatest magic trick, an illusion of probability emerging from a sea of timeless, reversible quantum possibilities. The quantum time crystal is more than a scientific marvel. It is a profound symbol. It shows us that in the heart of matter, there can be order that is not static, but dynamic. There can be constancy that is not stillness, but rhythm. And in that rhythm, in that endless, undriven tick of a quantum clock, we might just be hearing the faint, fundamental heartbeat of a universe where time itself is still figuring out which way to go. So, where does this leave us? Can time run backward at the quantum level? The answer is a fascinating, layered sort of. The laws themselves, at the most fundamental level we know, excluding possible CPT violation from the weak force, are time-symmetric. The quantum equations don't have a built-in arrow. Individual quantum processes can be manipulated to look like they are running backward, as with the photon and the quantum switch, or partially reversed, as with the ion crystal sensor. This is a direct operational rewinding. The principle of microscopic reversibility gets a quantum upgrade, accounting for coherence and uncertainty, and has been experimentally verified. However, when a quantum system interacts with a complex environment, information and coherence leak out and scatter in a way that is overwhelmingly probable to happen in one direction, toward greater disorder. This statistical tendency is what we experience as the irreversible flow of time. The backward processes are still possible in theory, but become astronomically, vanishingly unlikely for anything as complex as a cup of coffee or a memory. We are, in a profound sense, children of this statistical bias. The very existence of our matter-based universe might depend on a tiny time asymmetric flaw. Remember Andrei Sakharov's conditions? He argued that the cosmic dominance of matter over antimatter, without which we wouldn't exist, requires a violation of CP symmetry and thus T-symmetry in the early universe. Our arrow of time might be linked to the arrow of creation itself. As we wrap up our journey tonight, let this idea drift with you into sleep. We live in a world of spilled milk and fading memories, where time feels like a river carrying us in one direction. But beneath the surface of that river, in the silent, shimmering realm of the quantum, the water molecules are dancing in patterns that know no direction. Forward and backward are both written in their steps. The arrow of time may be the universe's most persistent and convincing illusion, emerging from countless tiny, reversible events. Your experience of time, the longing for yesterday, the hope for tomorrow, is real and beautiful. But perhaps it's also a glimpse of something deeper, a cosmic story written in two directions at once, of which we, for now, can only read one page at a time. If your mind has enjoyed wandering these strange paths with me tonight, if you'd like to support this channel of peaceful exploration, please consider giving this video a like. It helps more curious minds find their way here. And if you haven't already, subscribe to Hamif Sleep and hit that bell icon.
We delve into a new mystery each week, a perfect companion for your own journey into rest. I'm always so curious to know where in the world this community is gathering. If you feel like sharing, leave a comment below telling me your location and what time it is for you right now. Are you watching with the late-night stars, the early morning light, or somewhere in between? It's wonderful to feel connected across the globe and across time zones. Thank you so much for spending your time with me. I hope this foray into the heart of time has left you with a sense of wonder and calm. Wherever you are, whatever hour it is, I wish you a night of deep, peaceful, and restorative sleep. Good night, my friends. Sweet dreams.